Hello everyone, welcome to my channel Mathenthusiasm. Today we're going to look at a couple of limits that you can't quite use the L'Hopital's rule. The first one is limit x plus sine x all over x when x tends to infinity. Let's check the form before we apply the L'Hopital's rule. If we substitute x tends to infinity into the numerator and the denominator, then both of them will tend to infinity. So this is one of the indeterminate form. Okay, by L'Hopital's rule, we can differentiate both the numerator and the denominator. Then it becomes 1 plus cosine x all over 1. So what is the limit of cosine x when x tends to infinity? Is it 1, -1, 0, or anything else? We have no idea because the cosine graph is oscillating, so it does not approach any fixed value. What should we do? Let's split the limit into sum of two parts, which are 1 and sine x over x. Be careful about this limit. It is not equal to 1 plus 1, because the limit of sine x over x is 1 when x tends to 0, not infinity. Let's take a deeper look at the second part. Because sine x is between 1 and -1, therefore when x is larger than 0, sine x over x is between 1 over x and -1 over x. Because the limits of 1 over x and -1 over x are both 0 when x tends to infinity, so by the sandwich theorem, or we can also call it the squeeze theorem, limit of sine x over x is 0 when x tends to infinity. So the original limit is equal to 1 plus 0, which is 1. This is the first situation that L'Hopital's rule is not applicable. So what are the other two cases that it doesn't work? Let's look at the second example. Find this limit with exponential terms. Again, we check the fraction. It is in the form of infinity over infinity. So we can go ahead with L'Hopital's rule. Differentiate e to the power of x is equal to e to the power of x. And differentiate e to the power of negative x is negative e to the power of negative x. So we get this expression. Compared with the original limit, the numerator and the denominator are reversed. Well, this is not quite nice, but the form is still infinity over infinity. Okay, let's differentiate one more time. Then we get e to the power of x plus e to the power of negative x all over e to the power of x minus e to the power of negative x. Oh, this is exactly the same as the original limit. We're just looping around. So L'Hopital's rule is applicable. But even if you perform it by infinite number of times, you can never reach the limit. So what should we do? Let's change e to the power of negative x to 1 over e to the power of x. Now, we divide both numerator and denominator by e to the power of x. Then we get 1 plus 1 over e to the power of 2x all over 1 minus 1 over e to the power of 2x. When x tends to infinity, 1 over e to the power of 2x tends to 0. Therefore, the limit is equal to 1. Up to here, you may say that when we see something that can be differentiated finite number of times, say polynomials, then we go ahead with L'Hopital's rule. The answer is yes and no. The reason is that when we use the rule, it should be getting much simpler than other methods. What if you see the following? Will you change your mind? Limit x plus 1 times 2x plus 1 times 3x plus 1 all the way up to nx plus 1 all over x to the power of n when x tends to infinity. Here, n is a positive integer. Both the numerator and the denominator are polynomials with degree n, and it's also clear that they tend to infinity. But the problem is, after differentiating the first time, the powers decrease by 1, and the form is still infinity over infinity. That means we have to differentiate n times so that the leading term does not have x. On top of that, it's not easy to find the derivative of the numerator because it is a product of n terms. In this case, we believe that L'Hopital's rule works, but it is too complicated. Instead, we look at the structure of the limit. Consider the general case where both the numerator and the denominator are polynomials of degree n. The a's and the b's are constants. More importantly, the leading coefficients an and bn are both non-zero. Then the limit is simply an over bn. You can prove this result easily by dividing the numerator and the denominator by x to the power of n. You may also imagine that as x tends to infinity, the x to the power of n terms are dominating over all the others. So only their coefficients are important. Makes sense, right? Alright, let's go back to our original limit. How do we get the leading term in the numerator? In each bracket, we take the x term and multiply them together. So it is 1x times 2x times 3x all the way up to nx, which is equal to n factorial times x to the power of n. The smaller power terms are not important. We just use ... to represent them. Now, you may either use the result of the general case directly or separate the fraction. In both cases, we get the limit, which is n factorial. We have illustrated 3 examples which have their own shortcomings. Now, let me give you the following limit. See if you can work it out with the use of L'Hopital's rule or not. If you want to know more about this limit and other interesting problems in calculus, please check out the videos and the playlist on the screen and in the descriptions below. See you in the next video.